Okay, good afternoon, everyone. I'm one of the team members that Dr. Jose Yabor mentioned, dealing with water management. You know, as he said earlier, we work as a team of 3 or 4. We have his side, the business side, my side, water management, to some extent, some soil. And then Dr. Ravella as a soil scientist. But he's gone, and now we have 2 young dynamic soil scientists here to strengthen this team, Dr. Sharma and Dr. Bobby. You'll be hearing from them shortly. My presentation is just kind of an overview of what some of the socially disadvantaged producers, as well as the beginning producers and veterans, asked me to address when we're having a workshop with them. So with that in mind, the presentation is slightly skewed, different from what you have heard before. What you see there will be, I'll be discussing the hydrologic cycle or the water cycle, Earth's water balance, and the distribution, which is very important as we get into this time with population increase and the same amount of water, same amount of land. What are we going to do? Brief overview of predicted water shortage over a 100-year period, some irrigation history, talk about soil intake, and end up with a simple design. Later on, as we have more presentation, I'll get more involved with design. Next. Next slide, please. So here's the water cycle, a very general concept from Ralph Heath, former geologist here in North Carolina, Raleigh, North Carolina. And it's a simple thing. And then you're surprised to see the questions asked about, what is this, what is that, what is transpiration, evaporation, and so forth. So kind of give the young farmers or producers an overview of what these things are. That's one concept. Next. Here's another. Shows you precipitation, which is rainfall, that evaporates from your land or your, in this case, lakes. The difference between those two on the right will be 36. In this case, I'm using kilometer cube. And that goes as runoff. Goes back into your ocean. Even if it infiltrates into the soil, it pops up back sooner or later in the water source somewhere, which is basically the ocean. From the ocean, you'll have precipitation in the ocean, evaporation also from the ocean. If you subtract those two values, it equates exactly to 36. So what that is saying, the runoff is 36, what goes out is 36. It balances out. The hydrologic cycle is a closed cycle. And nothing comes out, nothing goes in, it keeps looping around. That's why it's called a cycle. It has no beginning, no end. We don't know where it starts, where it ends. Next, please. That looks like Dr. Yabor.
Oh, no, they want you to go through it.
All right, that's it. So we'll look at water distribution as such. I'm using the term water types here, but you'll see that over 99% of the water on Earth is tied up. It's in the ocean. We can't do much with that. We can go cruising, sailing, or whatever. And then you have the ice caps and glaciers. Good water, but we can't get to it. If it melts, it gets into the ocean. We have no access to that. So we look at the third one down, groundwater, surface water, soil moisture, atmosphere. That's what we have to play with on this planet we call Earth. So the groundwater is about 0.61%. Surface water, soil moisture. So all of that is what we have here on Earth to play with. But we have to be very careful of contaminating that water supply. So that's why water use efficiency and taking care of what we have You cannot dump chemicals just that way. It would get into your water and contaminate that. Next, please. Here's the distribution of our Earth's water supply. If you look back at, if you remember what we saw earlier, the ocean is 97.24%, ice caps and glaciers 2.14 thereabout. So everything is exactly the same thing as what we saw before with the teardrops, but here it's in a tabular form. If we take that out, we'll see. Please advance the slide. I guess my stuff is blocking my screen. No, can you go back, please? Yes. So of the freshwater supply, what you're looking at is ice caps, glaciers, and so forth, inland seas. And if you look at the lakes and atmospheric soil moisture, that's about a 1% factor. And we can distribute it to tell you where they are in the lakes and so forth. Next. This is a more recent water distribution diagram from Popular Science. It's a little bit dated, but it's newer than the older one. What you have had now is still the same because nothing is changing. All the water on Earth, this one is expressed in cubic kilometers, 1.4 billion. And the fresh water is 34 million. If we take out that 34 that you see there in that little red box, if you can see it, if you have access to it, but the little red box there, if you can take that fresh water out, can break it out into, again, frozen, which is the glaciers and ice caps, no use to us. That's almost 70%. 30% is the groundwater, which is where we are. Then followed by lakes and rivers and wetlands and soil moisture in the atmosphere. A lot of people may think that in the atmosphere that you have abundance of water supply. Not a lot. You just move from, because it's dynamic in such a way it falls out whenever it's ready. Out of that amount of all fresh water withdrawn for use on Earth, 70% is for agriculture. Industries will use 20%, and for home use, domestic home use is 10%. So that's where we are, right? So there's a need, according to these writers, that right now we are not doing too bad, but in the future, if population grows, climate change and other things, the supply will be much smaller than the need, right? And that's where the problem is. So what do we have to do? Efficient use of water, wise use, efficient design that we can recycle out water and make the best of it. Next, please.
Now that I've done this, you won't see me.
This is the evolution of the shortage over 100 years I referred to earlier. Shared with me with Dr. R.W. Skaggs, my advisor from NC State. Next, please. So in 1950, we look at this. This is where the water stress is. Saudi Arabia and I guess Tunisia. Some of you out there may be better at geography than I am. But you can see those little red spots. That's when the study started in 1950. Okay, next, please. In 2000, look at what is happening. See spreading, and look at where it's spreading. Next, please. 2025, I guess. So we are in this period right now, and the guys are still on track. If you notice what is happening, look at South Asia. Look at North Africa, East Africa, and then Peru in South America. So it hits the South America continent at this period. And if you look at what is happening, this is actually true. Next, please. So here we go now. So Africa is almost 2/3 or more of Africa is underwater stress. So there's a so it's on target or track based on what we are seeing here of a great demand for fresh water in the world. So far, we are okay in the US and most of Asia, but we have to look at our brothers and sisters in the other areas. So that's where the need for efficient water use, or if we can find some new water coming in, you know, it's not going to be a lot, but it may help some people somewhere. Next, please. History of irrigation. And, I'm just going to go quickly over with this slide. It started about 6000 BC in Egypt, and then later on 2000 BC, and then later on in Israel when we developed drip irrigation by the researcher, I think he was an engineer, not too sure, by the name of Blass. He developed the drip irrigation system. It was in Israel and other parts of the world. Next. Some irrigation facts. Approximately, we have about 16% of farmland is irrigated. And this irrigated land accounts for about 40 to 45% of production agriculture. So water is very important to us in agriculture. And there's a big competition between water and agriculture and industry. Who should get the water first? That's an ongoing discussion. Over 70% of water used in the global level is for irrigation. So irrigation is one that is using a lot of water on Earth. We can recycle it and we can maybe reuse it, or other people can treat it and use it again. It is estimated that irrigated acres in the world is about 600 million acres. So that's a lot of water being used. Again, remember the only source that we have for that would be the underground water or groundwater and some surface water and lakes. Water is required in sufficient quantity for crop growth. We need to know that first thing before we plant. It also helps to cool the plant and to maintain that turgor in the plant. That's somewhere up in Dr. Cohen's area as well. Next, please. Next slide. We can just quickly just give a quick estimate of cost per acre for using 8 to 10 millimeter drip. I should have removed this slide, but that's all right. We'll get into it in my next presentation. Next slide, please. So in addition to water, we're looking at the soil. So we must know these things. We have the food, energy, water nexus, which is the best thing nowadays. With clay soils, we have to look at how it behaves. From the diagram to the right here, whenever we have this piece of paper, if you're not looking at it now, it moves slowly, as we all know, with clay soil. There's a lot of pores, but they're so tiny that they do not transmit water readily. If you apply water at a higher rate, it will run off, and that we do not want that. That's wasting valuable water. Next, please. Sandy soil is the exact opposite. It goes down deep, it does not spread. So if your plant root is out of that zone, then you'll have some problems there. Water will move quickly, goes deep in the soil, and does not spread as wide as clay. So we have two problem soils on either side. Next, please. Loam. This is where we would like to be if we could have all our soils loamy soil. good for plants. Water goes in at a moderate rate, stays in the soil a little longer than sand, but shorter than clay. Easy access for the plant use. Next, please. Some types of irrigation, quickly. Surface, sprinkler, drip irrigation. We all know about these. Surface irrigation in practice a long time back, followed by drip, then was recently in the 60s, 65, drip irrigation. Next, please. Going back to that slide, we look at the efficiency of this. Not very efficient. Some say 40, some say 50% efficiency. The sprinkler overhead, 65 to 85% efficiency. Drip or trickle, as it's called, 90 to 95% efficiency. And that's where we're trying to go with the socially disadvantaged producers. If we it's quite much cheaper with drip and so forth. If they understand it, they can use it most effectively for good crop production. Next, please. What do we do with this? How do we test that soil? A very simple test. Thanks to one of my colleagues, a friend at NRCS. We can set it up with one of these Mid-Tolga water bottles. They get a little whatever I think maybe about a gallon. Can put an emitter inside there, and we can time it. We can measure the amount of what we know that the volume of the bottle. We can measure how much comes out over a given period of time. If it floods the area, we know that it's coming out too fast, so we'll have to try until we can heat that. This is something a small producer, socially disadvantaged producer, can do without buying an expensive infiltrometer to measure infiltration rate. Next, please.
7-minute warning.
Next. This is same thing. Just go through there. Next, please. Drip tubes. We have seen there. These are just small boring in the plant in the tubes. We have seen 2 different types there. Next. One method of applying drip irrigation, you can get a bucket, elevate it to some height, and then put your water through there and get into your plant. The height will depend on the pressure it takes to open that emitter. Recall that some of you listeners may remember that 1 psi is approximately 2.31 feet of head. Next, please. Or if you do not want to make frequent trips to that overhead tank, you can use this close to that tank and refill it easily. Or if it's highly elevated, you can feed it right into your drip tubes. There. Next, please. Typically, what we'll see is something like that at times using a standpipe. This shows that there's components of the drip system. We'll get into that in another presentation. Next, please. Sometimes the drip tubes are not pre-punched, so we have to buy these punchers that will allow us to put the hose where we want it. The reason for that is that you may have if you have a 24-inch spacing or 18 spacing, the drip tubes may not come into that spacing, so you need to punch the hose inside there and then fit it with those plugs or you put your emitters there. Next, please. Another type of system, in this case, is a deep well, and now you have a pressure tank. It's a much larger system, much more expensive. Next, please. Or you can do different zone. This one is just, when we took the picture, it was just being laid out. That's why the hose is so crooked. Next, please. This is an example on the field of a drip tape, flat drip tape. You're seeing a water drop there, and where the water goes, and exactly where you want it for in status tomato plant. So using much less water is going exactly where you want it, and so it's wise use. Next, please. There's also what is called a subsurface drip irrigation, where the water comes, the tubes are buried, and it comes up from the bottom up into the plant root. You can do so for cotton, soybean, etc. Next, please. The schematic of what you just seen in real life. Next, please. Different types of irrigation system. Lateral move. Next. Center pivot. Next. Hose drag or cable pull. Next. These are all different types of systems, and they're very expensive. This is all traditional where we do furrow irrigation. It wastes a lot of water if it's not trapped and recycled, but that's also commonly used, especially in developing countries. We must know in things, how much water to apply. We should know the crop need. Also know the soil you're dealing with. Is it sand, silt, clay, mixture of these things? We have to know. Remember that most crops, especially vegetable crops, are comprised of almost 90% water, so they need water to produce. Next. Select your system, again, similar to what we said before. How much water is available? Always know that. What is your water source? How much can I get from that source? How much do I need to put onto my plant? And look at the person applying that field. We call them irrigators. How skilled is that person to do this job? Next, please. How to determine what I call the runtime. This is a simple design. If we estimate that the crop's ET is 0.2 inch per day, for an acre of land, the crop will use 0.20 times 27,152. That 27,152 is gallons per acre inch. An acre of land with water in its soil about 1 inch deep, you get that. So if we, let's say for drip irrigation, we are just irrigating 50% of the land area. So that's where that 2715 is coming from whenever you get to look at that paper. If you're using 4-foot spacing along in the field, and the drip tape will always be calibrated to tell you how much they use, either 0.4, 0.5 gallons per minute per 100 feet of tape. In this case, you'll get 0.40, which is the volume from per 100 foot of tape. 10,890 divided by 100. Don't worry about that, what I'm saying here, if you listen to me or looking at the presentation. Next, please. Remember that 1080. Where is that 1080 coming from? There's 43,560 square feet in an acre. You divide that by 4 feet of spacing, gives you that 1080. Then, that's insane. That's over 2 miles of drip tape. So then you'd have to have several rows spacing along it so that you can have maybe 200 foot run, 300 or less. Next, please. So remember, we had 44 gallons per minute when we calculated that, which can change to gallons per hour. We have 2640 gallons per hour. Knowing the amount of water that you have to apply, divide, in this case, it was 2715, based on our calculation for the water demand, which was 0.2 inch per day. And the acreage, we now have 2,715 gallons of to apply. We can, how long do we apply? We look at the application rate, 2640 gallons per hour. divide that into 2715, our irrigation time is just a little over an hour. So we let the system run for an hour. Again, there are times because when during high peak summer, we may have to run it a little longer. Next, please.
The time is up, Dr. Gale, so can you summarize?
Yes, keep going on there. Let me summarize. These are given in what I need to look at, and this is this is a key factor. If you have no water, do not plant crops. So no water, no yield. If you do not plant to irrigate, do not plant the crop. Thanks for listening.